Hello, I want to share with you my understanding of the changes that Maxwell did to Ampere's law. I only go into only the first equation. So originally in Ampere's law, this second component here in this equation is zero. This part here doesn't exist, and this is a zero as this is. So from a let's look at the integration side of the formula. What it means is if we take the integration of all the magnetic field components around a closed loop called S, right? It should be equal to the integration of all the J that is normal to a surface A, which is defined by the closed loop S. So in this particular scenario, it makes sense because you see a J here, so you're going to integrate and get something, and that would reflect the result as H. However, if you, instead of that surface, you take another surface which does not intersect at all with the current J, then originally when you take that integration, since there's no J and there's nothing here in the original Ampere's law, the result of that would be zero, which is inconsistent with the other way. So what Maxwell did was he added a time varying component, which is the derivative with respect to time of the electric displacement into this equation, and that shows up here or here. The two sides are equivalent. And so when you do that and you check the integration over a surface which does not intersect with the current, you will now integrate the time varying part of the electric displacement, and the result should come out to be the same. So in summary, Maxwell saw a boundary condition issue with Ampere's law and postulated that we need to have this time varying component of the electric displacement. Why we add derivative of d with respect to time. So consider a system and there is some net inflow or outflow of current J, and within that system there is a charge distribution called rho. So what you have is anytime that you have a change that is equivalent to a current outflow to inflow that is equal to the change with respect to time of the total charge within that volume, and that's the change of versus time of the total charge. Applying the integral theorem, we convert the integration across the whole surface into the volume integration of the divergence of J. Now, so both sides is going to be integration with respect to the volume. And since the volume is fixed, so we can move the integration within the integration of the volume. And since rho is equal to the divergence of d, so it was proposed that the current density is not just J, but there is another component which is the derivative of displacement d with respect to time. So that's the reason why this derivative with respect to time of d is added to this. Thank you. Bye-bye.